but they're relatively new and recent. So that's I think that's the hypothesis that this author is trying to propose. Actually, I happen to know that a couple of people have been trying to. Why? Uh, okay. And the other, I've heard that the other people that trying to write a comment for this paper, but in Nature, but didn't got published to hear their voice. But in general, it's pretty interesting. They try to raise some
So these are the main authors of the work. And Nicholas Flament will be giving the talk on this particular topic next Wednesday. So he did his PhD in 2010 from University of Sydney. And then he was a postdoctoral fellow and research fellow in University of Sydney till 2016. Then he was a lecturer in the University of Wollongong in Australia, and then from 2019 onwards, he's a senior researcher. So in this particular topic, so if we look at the different the tomographical models of the Earth, so there are mainly two antipodal structures. So one is below Africa and another is below the Pacific Ocean. So these have been identified as the large low shear velocity provinces because the shear wave velocity in this region is 1% slower than the ambient mantle. So this difference in their shear wave velocity indicates that particular these zones, they are comparatively hotter than the other part of the mantle, and this can be not only due to the temperature difference, but also compositional difference can be responsible. So this is the tomographical model that have this image is of a tomographical model, and the mantle flow model that have been constructed by the other author. So that also gives a similar cluster. So we can see that this actually matches with the tomographical model. However, the structure is a little bit different. So the plate tectonics have shaped the Earth since by different various processes, and that is bound to cause some changes in the mantle dynamics as well. For example, the oceanic lithosphere, it subducts into the mantle, and in many cases, it goes to a great depth. And from other parts, the hot mantle plumes are rising. So the mantle is very dynamic. That also leads to the idea that these basal mantle structures must also be mobile, or they're not really stagnant. However, another suggestion is there. If we consider the large igneous provinces and the kimberlites through the different ages, So if we consider for the last 320 million years, so it can be observed that the major regions of volcanic activity, they are mainly concentrated on the margin of these mantle structures. So these are the structure from the tomographical model and the mantle flow model, if that is constructed through different ages. So these are the structures. So the high temperature and the low velocity regions are marked in gray, whereas these white regions, they have a lower temperature, whereas higher shear wave velocity. So if we look at these two images, what we see is the volcanic, like the eruptions, they are mainly concentrated on the edges of these structures. Now, this color bar that indicates the age at which the different eruption occurred. So according to that, it is color coded. So based on this observation, some hypotheses have been given that these structures, the basal mantle structures, they are stationary over the geological time. And this is actually in contrast to the observations that the tectonic plate subduction zones, they affect the mantle dynamics, and therefore there must be some change in these basal mantle structures as well. So now here the authors, what they have tried to see is the distribution of the distances between these basal mantle structures and the reconstructed eruption locations. So here various bins have been constructed and a cumulative frequency is taken. So this blue line, that is actually the empirical sample empirical distribution function. So it is the cumulative probability of the abundance of eruption locations, and this angle, this is the angle of the location of the eruption to the basal mantle structures. So if the value is positive, that means the it is within the, just a second. So positive value, it has been shown in another image. So if we go to this image, so this positive value are in these regions. So they are outside the positive value. Yeah, these positive values are the yeah. So these positive values, they are within the this low velocity zones, and these negative values, that will be away from the basal mantle region. And at the margin of these basal mantle region, the value is closer to 0. So based on that, these graphs have been drawn. So we can see that mostly the value, the highest frequency or the sharp rise in frequency is close to the 0. So this also shows that the main concentration of these eruptions of volcanoes are mainly at the margin, and they have and this range is constrained within a particular value. So we can see only at the closer to the margin, they have a higher value. So now for this particular study, so for this particular study, a large number of tomographic models as well as mantle flow models have been constructed. So these are the mainly mantle flow models that have been constructed. So 9 mantle flow models we can see. And there are 7 tomographical models that have been compared with each other. So I'll just explain this color coding first. So the orange, that is the true positive. So what they have considered is this Savani. So this tomographic model, they have taken it as the base model, and the other models have been compared in reference to this particular model. So this orange one, so this suggests the true positive, and these gray portion that suggests the true negative. And if we look at the green colors, so this green color code, it suggests the false positive. That is it, it is being compared to this particular model. And the green color coding, that suggests a false negative. So various different models have been compared, and what we can observe is that there are particular like both false positive and false negative are there in every model, but there are major overlap as well. So these overlaps can be clearly seen in this model. So, and obviously the tomographic models, they have a higher correlation, like they predict better. However, even the mantle flow model, they have like, they can predict to quite some extent. Now, the various factors, they control these model success. So these are the main 4 parameters that have been mainly considered for this study. So FA is the fractional area of the deep mantle covered by BMS in cluster space. So the total, like the only this orange color portion that is considered as FA. Now the fit, that is the accuracy, is calculated as the true positive plus true negative divided by the total area. So this is considered as a factor, and for mainly the best model would have a higher accuracy. So that they have compared in the next like plot, and this theta is actually the angle of the like this positive and negative angle that is in response, like in reference to the basal mantle structure. And this FS, that is actually this FS part I can't remember right now. So these are the main factors. Now, yeah, so FS are these parameters. So this one. Now, if all these models are compared, these 7 are the tomographic models, and then these are the mantle flow models. So this gray area that suggests the like range within which the tomographic models fall in, and based on this weight, the other model accuracy have been compared. So the best, like if we observe in many cases, for example, like we need the accuracy to be best. So to balance the accuracy, and also we must consider that the other parameters, they fall within the range. So in many cases, for example, this accuracy is better, like for C6. However, if we consider the other parameters, for example, FA, the range, the value of FA that falls outside this particular range. So therefore, it does not match with the tomographic model. So only these are the 3 points that falls within the tomographic model. So if we need to balance all the 3 parameters, the best model that can be that we can find is the C7 that have been discussed. So like according to this paper, the best fit is the C7 model. That is where the density at the like the basal layer density value is about plus 1.3% compared to the topmost density part. And so this is the best fit. And for that, the other models, like the other parameters have been optimized according to this value. Now, after fixing all the parameters, they have built a model. So according to this model, they have calculated the dynamic assembly of the African basal mantle structure through time. So this is calculated over time, and this is the current structure that they have found. Here, the blue colored regions, they are at a these are the low temperature regions, whereas the yellow and the orange color, they are the hot mantle structures. So here we can see that this part, this is the the oceanic crust that is subducting. So at these places, we can see that oceanic crust is being subducted, and as they go down, they are taking this dark blue color at depth. Whereas due to the downgoing slab, the mantle convection is operating, and as a result, in certain places, these warm zones are getting concentrated. So these are the upwelling hot mantle structures, and as it's rising, Then we can see that at a higher depth, the color is yellow. So these are the shallow part of the hot mantle structures. So this is the final structure that is given. So these blue colored ones, they are the subducting plates, and these are the basal mantle region, the structure, and the warm part of the like thermal structure. So what they have discussed at the end is the African BMS is not according to their model, it was not a very coherent structure till 160 million years. But the earlier paleoceanographical models and the other models that have been given prior to this study, they have already suggested that this BMS, they might have formed at approximately 200 million years. So the major difference of this model compared to the earlier models is that this model starts the predicting or the initial model is built at a older age. So they have constructed the model with the initial age of about 1 GA. So it actually extends further back in time, and therefore it can actually capture various geological events and how the plate boundary configurations evolve, etc. So that is the main difference compared to the earlier ones. So what they have suggested is at about 740 million years, so the cold slabs, they started to subduct, and as a result, these slabs progressively sank and accumulated above the core mantle boundary. Due to these subducting slabs, the African BMS, which was not a coherent body at that time, it was actually distinct portions, like distinct body. So those smaller parts, they aggregated and that started subducting at 740 million years. And this final structure that was mainly formed at about 60 million years. So at the end of the study, what they conclude is these structures, they are not stagnant, and they are they are actually affected by the moving mantle dynamics. And so the reconstruction of the past mantle flow, it shows that the structure of the earth is linked to evolution of its surface, and these BMSs have assembled, and they can actually assemble and disperse. So with the over time, when the due to the different motion of the continents, these structures can form and they can change over time. So that is the main conclusion of the study. What I did not include here, but in these models, they have been given in the supplementary, and the videos of the model evolving over time is also given in the supplementary. So that I can show it, but over time how these changes. So there are different videos.
When we go ahead, share the videos, please.
Yeah, so there are several videos. So yeah, so this is the, I'm not sure of the sequence, and I'll just play it. So these upper gray portion, they show the the continental outline, and these blue ones are the cold mantle structure and the hot mantle structure. Now these different structures, they have actually been clustered by the K-means clustering algorithm, and this is basically done based on certain parameters of this mantle. For example, like the temperature of the mantle changing with depth. So the K value is taken as 2, And therefore, the two different distinct clusters have been made. One is the hot that like they have been classified as the hot mantle and the cold mantle. So that can be seen here. So there are several other models as well. So it basically shows how the tectonical setting that is actually affecting the so this in this one the hot mantle structure can be clearly seen.
So what are the blue parts? So continental crust depth, what does it mean? So all
So
this.
this is basically the subducting part. So in the earlier model, they have shown the cold mantle, but here they did not like in this one. I don't see a cold mantle color coded. So these are the basically the continental crustal depth. It feels like the subducting plate is going down. It seems that way. Because otherwise it won't go to such a depth.
Yeah, go ahead. Are there more videos?
Yeah. And also what they have done is there are some
So what's the difference between the last two ones?
just a second. They are the mainly these two. Yeah. These two are there. So it's different. Okay, these are the mainly two different domains. The African mantle domain is this one, the C1. So basically the structure is a little rotated. So this part you can see, so this like basically it focuses on two distinct regions. So this is basically focused on the African mantle domain and this is the Pacific mantle domain. So this is more rounded in structure and this has a more sharper or elongated structure. This is below the African continent and this is below the Pacific.
Okay, go ahead. More videos?
Yeah. Yeah, they have like in the paper they have shown only but few of these cases. So these are the different mantle models. So in paper and what I showed, so there were particular like some of the mantle models, but here they have compared like all other mantle models as well. So with time they have actually showed how the configurations are changing in different mantle models, and then they took the best one and did a like better model there. So these are the ones like showing the true positive and true negative paths and different models. And this is the Savannah one, and others are being compared. Savannah, so being compared in relation to this particular model? I should. This is also beneath the African region. Yeah, these are the only videos that were there.
Okay. Okay. Thank you, Urmi, for witnessing this. I'm not a geodynamist. What I don't know is that they're trying to move the LSVPs for these two piles, as we can see in the different videos. But how could they still keep them, those two LSVPs, without being mixed in the rest of the mantle? That's not so clear to me, because is it, let's say, I probably didn't get the key point here, is that what's the role of the slabs? Let's say those blue points that they're showing earlier in the videos. So what's the specific role that they're trying to say here?
These blue color.
Mm.
Yes.
I mean the slabs. I think the crusts. Yeah, the one on the left. Yeah, that's what I'm seeing now. The 0 million years ago, which is right now, I think. So what other slabs play a role here? So how do they impact the LSVPs?
So basically, that is what I think they have explained here, that the cold slabs that are sinking down, so they are actually modifying the structure of the basal mantle structure, because when the cold part is being subducted, the dispersed warmer regions, they actually shift and sometimes they accumulate together. So actually the going down, like the subducting slabs, they actually shape the structure of the cold, like the warmer region. That is what they have said, like the
Okay,
tectonic.
so they shape the warmer region, but what are the LSVPs? Are the slabs part of the LSVPs as what they are trying to claim here, or they are not? They're just shaping the shape of the LSVP.
So these are the LSVP structures, these orange and red colored ones. So actually in the model, what they show is they are being restructured, and their structure is basically changing because of these subducting slabs.
So, but still, those LSVPs have, I said, their composition, not slabs.
Yes.
But they're just being okay. But I think that's more or less the consistent with what the people are trying to say before, like Ming Li's work. That is the slabs that shape the topography. The slabs as what the mantle flow, what they call the ambient mantle viscosity. But they are trying to say here that the LSVPs themselves are mobile. They are not stationary, and if it is true for large igneous provinces or kimberlites, they form at the edges of LSVPs. So at least that is self-consistent as where they got from the model. I think that's the argument that they're trying to get. So I'm not geodynamics. I cannot tell that how valid this geodynamic models do. I hope that we will have geodynamics on Wednesday to raise questions to ask about that, because so far as I see that people question, geodynamics try to question whether the stability of those LSVPs in these models, that some people think that it's not stable. It's very easy might be easy to mix with the rest of the mantle. I'm not sure because I don't know the details or why some people disagree about this uh, disagree with this work. Uh, so Ben has a question. The rough samples include large igneous provinces and kimberlites, and so how did they choose the samples? So
Actually,
yeah, why they only chose the young samples?
no, actually, I think they chose all the samples that they mentioned that they took these kind of samples. So this is the mainly the sample ages that you can see. So if they mainly took the large igneous provinces, the kimberlites, and some of the ocean islands. So only these kind of rocks like these kind of eruptions they chose. They only the from where the deep mantle plumes are involved, nothing else. So this is the main sample spread, and they took it from mainly two journals. So one is they have referred as J18 and another reference 40 like teen 18. So these are the mainly two references that they took their samples from. And they have mentioned earlier in the text what are like which data falls in these sample. I'll just show it in the method section. It is there. So then they have combined these two data sets and then they have plotted. So in the method section they have mentioned the J18. Yes, the J18, it has the ocean islands and the sea mounts, and the the LIPs are there, the oceanic islands and sea mounts are there, and kimberlites from all the kimberlite clusters. So these are the main kind of samples they took, and that is like the earliest age they took is from 320.
Okay, but the T18 choices from tab. I think that's the sticker that we had 2 years ago, maybe 1 year ago or 2 years ago. Those kimberlites, I'm not sure about the quality of those oceanic islands. So normally that you're trying, I, to me that this is a little bit how to say uh, because the reason that people try to argue that oceanic islands are part of the components coming from the LCPs likely due to their very high helium-3 helium-4 ratio. That's considered as very primordial components coming from the deep preserved within the LCP, for example. And that's the reason we're choosing that. But I didn't really see a reason that for this paper that how could they still keep those primordial signatures? If they could, is that the LCPs just move around very rapidly throughout the time. Um, but for kimberlite and large igneous provinces, so far as I know, that people are trying to link them to LCPs in the recent years. But I bet there are a lot of people in the community disagree about that. All right. So some more questions from our participants today? Okay, thanks Umi again. And then let's see the speaker on Wednesday. It will be 10 a.m. at Beijing time in the morning and very early in Indian Standard Time. So, okay, see you everyone on Wednesday.